Okay, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you again, Lord, for these students. Just pray that you just help us to understand a little bit more about complex functions today, Lord. We thank you for your many blessings to us. And we just pray for the weekend that's about to start that we could make a good use of the time, Lord, for your glory. In your name I pray. Amen. All right, so let me talk to you more about the story about complex differentiability and the Cauchy-Riemann equations. In particular, I want to study the following. If f equals to u comma v, which of course we can also denote u plus iv, all right? Well, if this is real differentiable, right? If this is real differentiable on a domain D, then and we also have that ux equals to vy and uy equals to minus vx at some point z naught in D, then f prime of z naught is equal to ux of z naught plus I vx of z naught. So this is theorem. Now we proved the kind of the reverse direction of this last time. Last time I said if you have a pair of continuously differentiable functions u and v, and if they satisfy the Cauchy-Riemann equations, then we proved that it was, no, excuse me, the other way around. We proved that if it's complex differentiable rather at the point, then that implies that it's real differentiable, and the Jacobian matrix had a very particular form. So this is the reverse direction to that. Okay, so let's just work it out here. Now, notation for the proof, it will be helpful if we say that ux of z naught is equal to a, and vx of z naught is equal to b, all right? So in order to not write quite as much, we'll do that. Okay? So what's this say then? Hence, the Jacobian matrix at the point z naught is equal to what? It's equal to ux at z naught, vx at z naught, uy at z naught, vy at z naught. That's just definition of the Jacobian matrix that you talked about last time. So if I've got a and b, and if I'm assuming the Cauchy-Riemann equations, what does the Jacobian matrix look like then? In terms of a and b, I have a. Where else do I have a? Because ux is equal to vy. That's, I'm assuming, the Cauchy-Riemann equation, right? So I've got a down. I got a on the diagonal. And I've got b for vx. What's uy? Well, uy is minus vx, right? So I got a minus b up here. Okay? Now, so the we have the differential at z naught acting on h is equal to the Jacobian matrix of f at z naught multiplied by h, all right? So what is that? Well, it's a minus b, b, a. And h is a vector, so it's h1, h2, let's say, okay? Now we can multiply matrices in 2 by 2 vectors. So what do we get? We get AH1 minus BH2, and I get BH1 plus AH2 right? By the way, I know this Jacobian exists because I assumed that we have real differentiability of the function from the outset, right? Assuming real differentiability means the Jacobian exists, among other things. All right, now let's rewrite this in complex notation. Our complex notation for this is that this is AH1 minus BH2 plus I times BH1 plus AH2. All right. So let's see, I can factor out H1. I've got A plus IB times H1. And if you look at it, I've got A plus IB times what? IH2. It's obvious that I've got AHH2 times I, right? Where's the minus coming from? What did I do? See, I changed this minus right here into a I squared to factor this like that. And then, of course, you can rewrite this. A plus IB times H1 plus IH2, or simply A plus IB times H. So the formula for the differential can be simply expressed as multiplication by a complex number. I claim that this complex number is precisely the complex derivative at z naught. Okay, so claim f prime of z naught is equal to A plus IB. So we have the limit as h goes to 0 of f of z naught plus h minus f of z naught minus parentheses A plus IB times h, all divided by the modulus of h is equal to 0. Now, why do I have this? That is the definition of real differentiability, that the Fouché quotient tends to 0. In other words, the change in f rather, is balanced out by the differential acting on h. The differential acting on h, remember, I just showed is equal to A plus IB times h over here. So I'm using this algebra argument over there. Now, my claim, though, guys, is this isn't, you're like, well, isn't there a difference between the limit in R2 and the complex limit? Well, actually, no, because the complex limit was defined in terms of modulus. But what's modulus? Modulus is the length of complex numbers as a two-dimensional vector. So it is actually exactly the same limiting process as we talk about in the study of real continuity. And more than that, there's a homework exercise you have which shows that if you have a limit of a complex function equal to 0, right? It's the same as it's interchangeable with the limit of the modulus of the complex function being 0. I can't do that for any number. 0 is very special in that regard. If I have the limit is 1, I can't interchange that with the limit of the modulus being 1, right? Because you got the e to the I theta stuff going on. But this, I can safely erase this without loss of anything here by one of your homework problems. Now, my next step is to observe the limit as h goes to 0 of A plus IB times h divided by h is equal to the limit as h goes to 0 of A plus IB, which is just what? A plus IB, right? So you can take the limit of the Fouché quotient up here, you can break it into two pieces, right? You can break it into the limit of this stuff and the other stuff. But the limit is that what I just circled in blue, right, exists. So it stands to reason then that the a plus ib is equal to the limit as h goes to 0 of f of z naught plus h minus f of z naught divided by h, but what is this? Therefore, f prime of z naught equals to what? Yep. But what is a plus ib? Remember the notation I introduced at the start of all this? It's, it's u sub x of z naught plus iv sub x of z naught. All right. It's almost the same argument we went through last time. The difference last time was I assumed complex differentiability at the start, and then I rewrote the complex limit to become a real limit, which then gave us the real differentiability. So this is the reverse argument. Any questions? So I'm gonna try to take a few minutes here for us to really try to appreciate what it means for the Jacobian matrix to look like that. Today, I'm going to try to really dig into that. But before I do that, I just, while we're here, we should stop and pause and notice. So if this holds for not just one z naught, but for say all the z naught, all the points in some domain, then I can just drop the z naught and write this as sort of an operator notation, right? An operator equation. So I have df dz. You could say that that's f prime of z, right? Now this you could reasonably define as partial x of u plus iv, right? At the point z naught. So a reasonable notation, I think you'll know what I mean if I write partial f partial x, meaning that you take the partial derivative of the u and the v component separately and you add them together. So one way now this is only true if the Cauchy-Riemann equations are true. You could consider functions in the of z and you can consider functions on the complex plane which didn't satisfy this, functions which were not complex differentiable, or as we'll soon be calling them, holomorphic. Actually, I already said that last time. What's holomorphic? Holomorphic meant complex differentiable. It was holomorphic at a point if there exists an open disk around that point on which the function's complex differentiable at each point in the open disk, right? And then if you had that it's holomorphic at each point in some domain, then we just said holomorphic on a domain. So, excuse me. How can you rewrite this in terms of y? See, vx. So this can also, you can also write df dz excuse me, is equal to minus I partial f partial y. See, because that would be minus I times uy plus I vy, which is what? Minus I uy plus vy, right? Which is equal to what? By Cauchy-Riemann equations, vy is ux, and uy is minus vx, so that minuses cancel, and I'm back to where I started. And this calculation is reversible, of course. So for a holomorphic function, complex differentiation just amounts to differentiation with respect to x, if you write the function in terms of its real variables. Or you could think of it as differentiation with respect to y, where but you have to multiply by minus I, as it turns out. There are other ways of remembering, but actually, these equations I just wrote, so df dz equals to partial f partial x, and df dz equals to minus I partial f partial y. These are actually, you get right down to it, these are just slick notations for the Cauchy-Riemann equations. Right. And there are other ways of looking at the Cauchy-Riemann equations. There's a couple pages in my notes devoted to deriving them in polar coordinates. I won't even talk about that except to say that. But you can also derive them you can find them in polar coordinates as well. Any questions? Let me show you what that means. Like here, for example, e to the z. Remember what it was? It was e to the x cosine y plus I sine y. So d dz of e to the z is partial x of this, which of course is it is a very efficient way of looking at what the Cauchy-Riemann equations are. Now, in order to make that calculation, I have to know that e to the z is, in fact, holomorphic, right? That it is complex differentiable at each point in some domain of consideration. But anyway. So a definition I should share with you before I get carried away here. Definition, if you have f going from the complexes to the complexes, and f is holomorphic on the whole thing, then f is said to be entire. An entire function is a function which is holomorphic on the whole complex plane. And we denote this, we say f is an element of kind of a funny looking O. F is in the OC. Sorry. This is the set of all entire functions. You can also talk about functions being holomorphic on a domain D. So f holomorphic on D. Holomorphic. That means that f is an element of, their notation for it is OD. So OD is a set of all holomorphic functions over some domain. It's a very special set. It has nice properties, like the sum of holomorphic functions is again holomorphic. The product of holomorphic functions is again holomorphic. All right? Because we have product rule and we have linearity of the complex derivative. So in fact, this set of functions, OD, it's known as a ring. It has both a multiplication and an addition, which is closed back in it again. It's a ring of functions. Let's see here. All right, so there's that. Here, so at this point, I want to show you I'll show you how special holomorphic functions are. This little story arc here kind of shows you just how special the complex differentiability over some domain is. So this was the theorem we skipped earlier, theorem 2.1.28 on page 28. Here's what the theorem says. It says that if you have H, which say from D some subset of R2 to R is suppose let this be continuously differentiable. With the gradient of H equals to 0, right? And here I'm assuming that D is a domain, which means what? Open and what? What else? Connected, right? Open and connected, a domain. So if you have a continuously differentiable function on an open connected set, and if the gradient of H is 0, what does that imply about H? In other words, H is what? Constant, right? H is constant. So here's the proof of that. So picture picture this open connected set. Here's my D, right? You pick any 2 points you like in the set. Say here's point P and here's point Q, whatever. The fact that it's connected, what does that mean? I can break it up. I can find a broken line segment, a polygonal path, right, which gets me from P to Q, right? And so let's let gamma be one of those line segments. So gamma's a line. So gamma is a mapping from, let's say, T naught to T1, of course, to the to D. It's in D, which is a subset of C, of course, and gamma of T naught is P. Gamma of T1, let's say, is equal to P1. I'll just call this P1. It's one of the linking points, right? Certainly, it's a smooth path. You can differentiate a line, right, with respect to the time parameter. So if you consider then H of gamma of T, right, you can consider that this is a differentiable function, right? It's certainly a differentiable function, right? Because we assume that H was continuously differentiable, which means, among other things, that it's got a Jacobian matrix. And I mean, we can differentiate it basically in the chain rule from calculus 3 holds. So I can differentiate this, right? What do I get? Chain rule. Chain rule tells me that that's the gradient of H evaluated at the curve, dot product with the gamma dt. But gamma of T, this is in D, right? By construction of the polygonal path. That's what it means for it to be connected. You can find a polygonal path, that each line segment in the polygonal path is inside the connected set. So this, by assumption, then is what? Zero. So this is 0. But T is an element of what? T is an element of T naught to T1, which is an interval of real numbers, right? This is an interval of real numbers. So that's a connected subset of real numbers. If we have the derivative of a real valued function on a connected subset of real numbers is 0, then that means that the function is constant. So it follows then that's a connected subset of R, right? And so that implies then that H of gamma of T naught is equal to H of gamma of T1, which is to say that H of P is equal to H of P1, right? And then you just repeat this argument on each segment. Right, but P and Q are arbitrary, so that shows that H is constant on the domain. This is a pretty standard argument. I would probably show it to Calc 3 if I don't forget. Okay, so there you have it. That's what's on the final, so you know. Welcome back, Sharon. So, theorem. If f prime of z is equal to 0, and if f prime of z is equal, well, excuse me. Let me not. What is the theorem I want to tell you? If f is analytic on a domain, and f is real valued, f is constant. Here's an example. if f not equal to 0, 0 is too obvious. Of course, if f prime of z is equal to 0, essentially by two applications of this theorem, you get that f of z is constant. But it's more interesting than that. If f prime of z, let me use my terminology. If f is an element of the holomorphic functions on a domain D, and if f is equal to the real part of f, in other words, this is a snazzy way of saying that f is real, then f is constant. How does the proof of this go? So what is, so the gradient of u is equal to what? Ux comma uy, right? And the gradient of v is what? Vx comma vy, right? That's just calc 3. If we can show that those are 0, then the theorem we just proved up there takes over and shows you that u and v are separately constant. Hence, their complex combination is constant, right? So why are those gradients 0? Ux is equal to vy, right? And uy is what? Minus vx, right? What does this say? U plus iv is equal to u. What's that say about v? It is 0. Consequently, this is 0, this is 0, and so the gradient of u is equal to the gradient of v is equal to 0. And then the previous theorem takes over and shows that u and v are constant. So if I have a holomorphic function on a domain which is real, it's constant. Very similar argument shows that if you have a holomorphic function on a domain, if you have a holomorphic function on some domain which is imaginary, it's constant. There are like a dozen different twists on this. If you have a holomorphic function, I forget. There's like about 15 different ways to modify this theorem and get this constant criteria. It doesn't take much to make a holomorphic function be constant. Okay. You're like, well, this is all great, but you're using these words, and I don't really understand what they mean. What is holomorphic? Okay, fair enough. I mean, what is it, right? I mean, we have ways to calculate the derivative, right? But what is it? So let's take a step back and look at that some now. What is the Jacobian? What was the Jacobian matrix for a function from R2 to R2? What is it? Remember we looked at last time, it gives you the local approximation. If you look at the linearization of the function, it gives you a local approximation to the function, right? So the Jacobian, what it's really doing is it's revealing how the function behaves at the infinitesimal level. If you allow me that heuristic. Let me just make that explicit for a second here, and then we'll talk about it. So, and what I'm about to write, it's not just for complex variables. This is true just for points. If I have f is equal to, u comma v, then I have f of a plus h comma b plus h1, b plus h2 is approximately equal to f of a comma b plus the Jacobian of f at the point a comma b times h1, h2. So this gives us like a linear approximation to the function. Now, so let's look at this. We've got the Jacobian of f, but let's specialize. Assume the CR equations hold, all right? So in other words, assume that the Jacobian of f at the point z naught has that special form a minus b, ba. What does that mean? Well, I would point out to you that we can take this and we can rewrite it as follows. We can rewrite this as 1 over a squared plus b squared. And then I've got, excuse me, idiot. Sorry, square root of a squared plus b squared, right? And then I have like a over the square root of a squared plus b squared, minus b over the square root of a squared plus b squared, b over the square root of a squared plus b squared, and a over the square root of a squared plus b squared, like so. Now, it turns out that if the matrix has this form, if I call this matrix, say, R, all right? If I call that matrix R, you can prove that that matrix satisfies the following. It satisfies R transpose times R is equal to the identity. In other words, that's what's known as an orthogonal matrix. So what does that mean? That means that that's either a rotation in the plane or it's a reflection and a rotation, depending on the, It may have to be a rotation here because I've assumed the Cauchy-Riemann equations hold. But anyway, so that's not hard to... Anyway, that's just an identity. I mean, you can check this identity, check the transpose, multiply, you get back to identity matrix, whatever. This, in the front, is known as a dilation. It just gives you a rescaling. So, in short, at an infinitesimal level, all these, if the function is complex differentiable, what that means is that infinitesimally, all it's doing is just kind of like rescaling vectors and maybe rotating them a little bit. So I will show you that implies that the function's what's called conformal in a future lecture. Basically, that if you look at two curves which cross in the domain, and if you look at their image under a complex differentiable map, then the angle between the paths in the domain matches the angle between the paths in the image. That's called conformality, or the preservation of angles between intersecting paths. So that's, I mean, you can already start to see that here. But this, you can actually make this cosine theta, and you can actually make this sine theta. Okay, that's a reasonable thing to say because those quotients have to be, the absolute value of them has to be less than 1 if you look at the formula, right? So it's reasonable to identify them with sine and cosine. But anyway, what's the determinant? While we're at it here, what's the determinant of the Jacobian of a complex differentiable function? I'll use the AB notation. It's a squared plus b squared, right? What is that in terms of the derivative, the complex derivative, though? I submit to you that that's exactly the modulus of f prime of z naught, right? Squared. So the determinant of the Jacobian of a complex differentiable map is simply given by the square of the modulus of the the complex derivative. It's very simple. The relation, right? So what's that say? That says, obvious theorem. If f prime of z naught is not equal to 0, then the determinant of the Jacobian of f at z naught is not equal to 0, right? Now, when you take advanced calculus 2 years from now, or right now, I guess most of you won't probably be here. You lost your chance. Oh well. But one of the theorems we go over in there is the fact that there's this thing called the inverse function theorem. Right? And the inverse function theorem says simply this. You can find a local inverse to a function from Rn to Rn if the determinant of the Jacobian is not equal to 0 at the point in question. And we need some technical blah, blah, blah. We need continuous differentiability near the point. So this actually then shows you, if you use the inverse function theorem in advanced calculus, that, and okay, is this really an if-then statement? No, this is an if and only if statement, right? Because it's an identity. I mean, assuming, of course, that the function has, you can write these expressions meaningfully. But so that brings us to the inverse function theorem for complex analysis. Which, in the interest of not running around like a chicken with his head cut off, I'm going to project, if you don't mind. Also, because the details of what I'm about to show you is mostly advanced calculus, but I think it's important to actually see it. But it's advanced calculus of the most innocuous kind. Basically, what I'm about to tell you is that the Jacobian of the inverse function is the inverse of the Jacobian of the function that you're given. It's really, really, seems like I didn't say anything, right? I did, though. Let me show you what I'm talking about. You have some homework problems on harmonic functions. You can try those before I talk about it. It's not that big a deal. What does it mean for functions to be harmonic? I know the weekend's about to start, so let me just say a word on that to give you a kick in the right direction. Harmonic just means this. uxx plus uyy equals to 0. If this equation is satisfied for u on a domain D, then u is said to be harmonic on D. It's a harmonic function. So I'll let you read about that. You read more, but that's essentially it. That's what it means to be harmonic. And it turns out that the u and the v in the complex if a function's complex differentiable, the real and the imaginary components are automatically harmonic. It's just a short calculation from the Cauchy-Riemann equations. In particular, well, let me not do it. Our time is limited. Let me stay on task here. I'm just saying, don't be scared of the harmonic homework problems. Go ahead and try them over the weekend if you have time. And then when I talk about harmonic functions next class, it'll make even more sense. Okay? So we just worked out this little, stop it. I wish I could save settings, just remind myself. I'm going to look at it this way. I think I need, this must be really painful for you guys to watch. Oh, I already have enabled scrolling. All right. So as I was just telling you, oh man. If f is complex differentiable, the Jacobian of f, the determinant of the Jacobian is the modulus of the derivative squared. All right. And here's the theorem. If f of z is analytic on a domain D, all right, and if you have non-zero derivative at one point, then there is a small disk u containing the point such that the restriction of the function to u is 1 to 1. And the image then, V, is the image of image of U under F, F of U, is open. And the inverse function, F inverse from V to U, is analytic. And analytic here is, that's the word that Gamelin uses. I would say it's holomorphic, okay? It's holomorphic, and it satisfies the derivative of the inverse function at the function's value is simply 1 over the derivative of the function. All right. So I'm going to outline here a proof from advanced calculus for you. Basically, the point is this: if I have, first of all, if I have this condition that f prime of z is not equal to 0, that then means that the determinant of the Jacobian of the matrix is not equal to 0, which means by the inverse function theorem of advanced calculus, there exists an inverse function. All right. So I know that the inverse function exists, and then I'm just basically working out the formula for you in terms of the AB minus BA pattern stuff. The left regular representation of the complex numbers, whatever. But okay, so where am I? So you have that there is some inverse, so G composed with F is the identity on U. So the chain rule from advanced calculus says if you differentiate that, it amounts to saying that the Jacobian of G at the inside function F times the Jacobian of F at P is equal to the identity, all right? Which is to say that this is the inverse of that matrix, right? If you have plotted two matrices equal to identity, one of them is the inverse of the other. So I just say, okay, so let the Jacobian of F be our usual A minus B, BA. And then that means that this other thing here, the Jacobian of G at F of P, will be the inverse of this. But the inverse of this is it's a 2 by 2 matrix. We know how to invert that. There's a 2 by 2 inverse matrix formula, right? You should know that, even if you haven't had linear. This is something you should memorize. It's important to know. So that's 1 over A squared plus B squared. The diagonals flip, and you put minuses on the off diagonals. But A flipping to A is just A, so it's A, and then B minus B. So there it is. There's the inverse of the Jacobian, which corresponds, of course, to the derivative of the inverse, because we know that there's a connection between the pattern of the Jacobian matrix and the corresponding complex function, right? So I'm using that thing we looked at earlier today. But here it is. The Jacobian of G of F of P is this lovely expression, A over A squared plus B squared, And so then, using the theorem that I derived earlier today, that means that the G prime of F of P is equal to 1 over A squared plus B squared times A minus B, because this complex number corresponds to the matrix I just wrote under the usual correspondence of A and B in the 2 by 2 matrix. That's the complex number which corresponds to. But if you rewrite that, that's just 1 over A plus IB if you undo the multiplication by the conjugate. But that's 1 over F prime of P, and there you have it. That shows you that indeed the derivative of the inverse function is 1 over the derivative of the given function, right? But they're not at the same point. The derivative of the inverse function is at F of P, right? That's equal to 1 over F prime of P. So that you're comparing P to F of P in the derivatives. So it's not, Oh, here's what I was just talking about a minute ago, right? Now, this is important because this means that we can do implicit differentiation. Right? So, for example, let me put this away. How do you, power rule. We've seen z squared differentiates to 2z, right? But how would you differentiate z to an arbitrary power, and how would that work, right? So, an example of how this works. If I look at the log, log of z is equal to, let's say, w. Go back. Sit back. Go back. Back, I say. Oh, man. World-class IT. All right, so e to the w, sorry, I should be quiet, equals to z. But then we know the chain rule, right? So I guess you could do that. I mean, well, so if I differentiate this implicitly, I get what? I get e to the w dw dz is equal to 1. So again, d dz of log of z is equal to 1 over z. But I am using the inverse function theorem here if you think through it carefully. But basically, we recover those usual arguments from Calculus 1 at this point. How do you differentiate z to the n? Or z to the c power, let's say? By the way, that derivative only makes sense on the slit complex plane. While I could define the log in principle on the punctured plane, this is really only for c minus. Otherwise, I have a discontinuity. But complex differentiable implies continuous. So if I have a discontinuity, you know something's up. So basically, we lose a branch. We lose that one ray, the negative real axis there. How do we differentiate this? Well, this is really, what's the definition of z to the c? It's e to the c log of z, right? But I could be more vague here. I could say, well, an arbitrary branch of the log. So it's also true that, you know, if an arbitrary branch of the log, which I'm just using a script L for at the moment, so L of z equal to w, that it also implies that z is equal to e to the w. And so same calculation holds through. It's just there, the place it holds is possibly different. I mean, there's got to be some ray that you lose. It's going to be some slit complex plane. If you want to be more explicit about it, you could talk about the log sub alpha, where we lose the alpha ray, right? But anyway, so then do what? Chain rule, right? So this is e to the c lz times d dz of c lz, which is what? E to the c lz, and then what? C over z, right? But you can rewrite that as c e to the c lz, L of z, times e to the minus L of z. And so you get c e to the c minus 1 times L of z, which, by the way, is c z to the c minus 1. I won't get this. I don't get this for the whole complex plane for arbitrary c, but I do get it on the domain on which the logarithm, this particular branch of the log, is holomorphic. Any slit complex plane, we can achieve this. If you want this equation for the whole complex plane, then you need something special about c. You need c is like, for example, an integer. That'll do. There we don't need, I mean, you can define integer powers on the whole plane, right? Polynomials are entire. Z to the I is not entire, I don't think. If it is, I'd have to think about it. Anyway, so, hey, all of a sudden we've got all of our favorite examples from Calculus 1, which is pretty awesome, right? So next time I will talk to you more about harmonic functions and about the issue of the conformality. Then we'll talk about fractional linear transformations, and then, before you know it, we'll have the ultimate form of classroom interaction. Yes. A test, yes, test 1, yes.
Oh, so what's the next homework due?
Oh man, I was thinking class ended at 45 after. I'm an idiot. I've been hurrying for no reason.
You're on time.
I'm on time. I feel dirty. I feel like I could squeeze I could get like another 3 minutes out of today. But I'll tell you what, I'll just cut it off here and let you go. Unless you have a question. Sharon's like, don't ask a question. Michael, I hate you. Go ahead, Michael.
Everybody else can. But I wanted to know, what is the connection between what we're doing here and calculus? Are we supposed to think of what we did in calculus as this being the theory behind what we're doing in calculus? Or is this just an alternate way of looking at what we did in calculus?
So what's the connection between this and Calculus 1? Well, the connection in some sense is that, and that's a good question. I mean, many arguments can be duplicated. So there are a lot of parallels, but there are other things which just don't really have an analog in Calculus 1, like this theorem we had earlier about if the function's real valued, it has to be constant. I mean, there's something really, really special about the function being, you can turn it off, yeah, complex differentiable, as we'll see as we go on.